Alright guys, welcome back to a new video. Today we're going to be talking about some more runtime in data structures and algorithms. Now before I continue and start the video, I want to say if you're looking for a job or internship, check out the top link in the description. I think it'll really help you here. But without further ado, let's get right into this. Runtime, we have big data. And if you haven't watched the previous video, it was the introduction to runtime, what it is, how it can help you, and what are the benefits, right? If you know already what runtime is, what asymptotic notation is, then we're just going to get right into it here. So the first subtype of this notation we'll explore is the big data. And this is denoted by this symbol. It's basically the theta symbol in Greek. We use big data when a program has only one case in terms of runtime. But what exactly does that mean? So take a look at the pseudocode for the function that prints the value. Function with the input that has a list of size n, okay? For each value in the list, print the value. So the number of instructions to the computer has to perform is based on how many iterations the loop will do, because the loop does more iterations, then the computer will perform instructions. Now let's see how many iterations the loop will do on the dependent of the value n. So the size of the list and then the number of iterations. So basically for the size of for your n value, it loops that many times. So we can see that in every case with the list of size n, the program has a runtime of n because the program has to print a value n times. Thus we would say the runtime is theta of n. Let's look at a more complicated example. In the following pseudocode program, the function takes an integer n and counts the number of times it takes for n to be divided by 2 until n reaches 1. So function that has an integer input n, okay, so you set a count variable equal to 0, loop while n is not equal to 1, increment count, and then you do n equals n divided by 2, return count. So basically, let's say we have 10, so it'll keep looping 5 times for that. So now let's see how many iterations the loop will perform based on n. So if it's n is 1, it'll just do 0. If n is 2, it'll just do 1 time. If it's 4, it'll divide it by 2 times. 8 is 3 times. 16 is 4 times. You see how it's exponential? So as we can see in every case with integer n, the loop will iterate log of n, right? Log of n times. Now, however, because we drop constants in asymptotic notation, we would say that the runtime of the program is theta of log n, because you're dropping the base 2 here. Now, but what happens when there are multiple runtime cases for a single program? We'll learn about that in a future exercise here. So I highly recommend watching this video by Code Academy, teaching you the big data notation. But let's go ahead and look at some common runtimes here. So what are some common runtimes? We have theta of 1. So this is a constant runtime when a program will always do the same thing regardless of the input. For instance, a program only prints hello world, runs a theta to the 1, or like big O to the 1, because the program will always just print hello world. Log n, the logarithmic runtime, you will see this runtime in search algorithms. So if it keeps cutting it in half, that's where you get log of n from. Just n is the linear runtime. So this means that you'll often see this when it has to iterate through the entire data set. So if you put in 10 pieces of data, it has to go through all 10 of those. That's when it's linear, right? So the input is proportional to the output. And then we have n login. So you'll see this in sorting algorithms. So n login is for used for sorting algorithms there. And then n squared, this is an example of a polynomial runtime. When n is raised to the second power, it's known as a quadratic runtime. You'll see this runtime when you have to search through two-dimensional data sets like matrix or nested loops, right? Next we have, let's see, it's getting even faster. So it's 2 to the n. This is an exponential runtime, so you'll often see this in recursive algorithms. So don't worry if you don't know what that is yet. Yeah. Okay, and then this is the factorial runtime. So you'll often see this program when you have to generate all um, of the different permutations of something. For instance, a program that generates all the different ways to order the letters A, B, C, D. So this is just basic, just one time access, one time print anything one time. That's your constant one. This is used for searching algorithms. It keeps cutting it in half. This is your linear runtime. Basically, it's the input is proportional to the outputs. This is n login. This is usually used for the sorting algorithms here. So it's a little bit more exponential. This one is used when you're looping through like matrices or nested loops. This one you're going to use for recursive algorithms, and then finally this one is for permutations. So big omega and big O. Sometimes a program may have a different runtime for the best case and worst case. For instance, a program could have a best case runtime of O to the 1 and a worst case of O to the n. We use a different notation when this is the case. Or I'm sorry, theta to the 1 and big theta to the n. We use a different notation if this is the case. We use big omega, or this little horseshoe symbol, to describe the best. Let me go ahead and make it bigger here for you. So we use big omega to describe the best case and big O to describe the worst case. So take a look at the following pseudocode. Function, so without even looking at the answer, just tell me what the runtime is. If you want to pause it real quick, go ahead and pause it. But okay, function with the input that has a list of size n. For each value in the list, if value is equal to 12, return true, else return false. So what is the runtime for this? Obviously, if you've been following along, it's n, right? So how many times will the loop iterate? Let's take a list of 1000. If the first value was of the list was 12, then the loop would iterate once. However, if 12 wasn't in the list, it would loop 100 times or 1000 times. So if the input was a size of list of size n, the loop would iterate anywhere from 1 to n times, depending on where 12 is in the list, if it's in the list at all, right? So thus, the best case, it has a constant runtime, and the worst case, it has a linear runtime. Now, here are the many ways we can describe this. So the program has a best case of runtime to the big theta of 1, worst case of big theta of n, has a runtime of big omega of 1, and then big O of n. So you may be tempted to say the following: this program has a runtime of theta to the n. However, this is not true because the program does not have a linear runtime in every case, only the worst case. In fact, when describing runtime, people typically discuss the worst case because you should always prepare for the worst case scenario. Oftentimes in technical interviews, they will ask you only for the big O of a program. Now that you know the difference, let's dive into more complex programs. So this is adding runtimes. So sometimes a program has so much going on that it's hard to find the runtime of it. So let's take a look at the pseudocode at the program here that prints the all positive values up to n and then returns the number of times it takes to divide n by 2 until it is 1. So, so there's a lot going on here, right? So how do you realize what the runtime of this is? So function that takes a positive integer n, set the variable I equal to 1, loop until I is equal to n, print increment I, set the count variable to 0, loop while n is not equal. So you're just combining two programs, right? So rather than to look at this program all at once, let's take a look at the two chunks. The first loop and the second loop. In the first loop, we iterate until we reach n. Thus, the runtime is theta of n. However, the second loop, that demonstrated in the previous exercise, runs of log n. Now we add the two runtimes together, so the runtime is theta of n plus theta of log n. However, when analyzing the runtime of a program, we care about the slowest part of the program, and because theta of n is slower than log of n, we would actually just say that the runtime of the program is theta of n. It is also appropriate to say that the runtime is big O of n because it runs in theta of n for every case. Then it also runs in theta of n for the worst case. Most of the time people will just use big O notation. So I personally am more familiar with big O notation. It's a lot easier to just remember like the worst case. So basically whatever part of the program is the slowest, that's your runtime for any program. And the little tip here is for just a single for loop. It's usually just O to the n, and then if it does this, like if it's looping n while it is not equal and then keeps dividing n by 2, then that's log of n. If it's two loops together, that's going to be n squared. All right, so here's a review of everything that we've learned. So we use asymptotic notation to describe the runtime of a program. The three different types of asymptotic notation are big data, big omega, and big O. We use big data to describe the runtime if the runtime of a program is the same in every case. The different common runtimes from fastest to slowest are theta of 1, theta of log n, theta of n, theta of n log n, theta of n squared, theta of 2 to the n, and then theta of n factorial. So these are the different common ones, right? And it goes from, like, of course, fastest to slowest. So we use big omega to describe the best case and then big O to describe the worst case. So we typically describe a program's running time in terms of big O. When finding the runtime of a program with multiple steps, you can divide the programs into different sections and add the runtimes of various sections. Then you take the slowest runtime and use that runtime to describe the entire program. Now, when analyzing the runtime of a program, we care about the part of the program that is slowest always. Okay. Next, I believe we have a quiz here. All right. So an identical algorithm written in two different programming languages will have the same big O runtime complexity. True, because big O is meant to be coarse enough to communicate between different programming languages. Suppose we had a function that iterates through a collection of data once to find the minimum value, and then again in a separate iteration to find the maximum value. What would be how would you write it, the big O runtime complexity? Let's see, and then again in a separate iteration. So separate iteration means big O of n. Okay. Suppose we had a function that performed one step for each algorithm in a collection of input data. What would be the big O time complexity of this function? Perform one step for each algorithm of a collection of data. So it'd be, I believe, linear as well, because if you have 10 elements, it would do it 10 times. Suppose we had a function that took a list of data as an input, For each element, the function compared it to all of the other elements in the collection. What would be the big O runtime complexity for this function? So if it took all of those and then compared it to everything else, it would be, I believe it would be 2 to the n, right? So imagine a list of 5 elements if you would need to compare. Okay, so it'd be quadratic actually. It makes sense. What are the constant factors such as 2n and lower order terms 2n? While ignore. We cannot be sure the significance of the lower as they relate to constant factors. As the input of the function goes towards infinity, lower order terms and constants cancel each other out. We do incorporate it as an input grows lower order become insignificant. Yes, they do become insignificant. And then with big O notation, we evaluate a function's runtime based on the size of the arguments, the number of variables, I believe the size of the inputs. Why don't we use time-lapsed 5 minutes, for example, as a measurement? Different units of measurement make this infeasible. Time is a social construct. Time is not relevant to quantum computing. Algorithms provide, yes, different programming languages, different CPUs. You cannot be general enough with the time-based. Select the correct order of runtime complexity from most efficient to least efficient. So of course it would be big O of 1 log n, and then n squared, and this. Yep. Final question, a function that only perform the operation like 6 plus 9, which would be the runtime complexity? I believe it would just be constant because it's just one time, one thing, right? 88%, the best commander here. If you enjoyed, please like and subscribe. I'll see you in the next one.